Welcome to Maths with EJD. In this video, I'll be talking about difference operators. That's numerical differentiation with difference operators. Now, in the previous video, we had considered numerical differentiation using finite difference method. So I find it important to also talk about some difference operators closely connected with those uh, finite differences for sure. Now, in this video, I'll be talking about the operators, and I think I should do one more video to actually see how you can apply them in solving problems. So let's move on. Um, so first of all, let's go for an overview of difference operators. So first of all, difference operators are fundamental tools. They're fundamental tools in numerical analysis, particularly in finite, particularly in finite difference methods for differentiation and interpolation. And interpolation. These operators define discrete, discrete analogs of differentiation. Hey, so let's go ahead and begin to talk about them. Under finite difference, we already talked about forward difference, backward difference, and central difference. But here we are talking about their operators. So let's start with the first operator we can use. Or should I? Okay, well, let's just go ahead and should I talk about types of operators? Yeah, I think it's important if I say types of difference operators. I think that's a nice way to go. Types of difference operators, just like we did for finite difference. So first of all, we have the usual, first one is the forward difference. Just like forward difference was the first one we considered. Here we have a forward difference operator, and each of them has a symbol attached. So this looks like this. Is this triangle or something like that? So the triangle with the tip up, so to speak. So that's the forward difference operator. Okay. So the forward difference operator, this should we call that delta? I'm not sure. Is defined as this f of x equals f of x plus h minus f of x. So it bears close resemblance with what we did under finite difference, where forward difference uses x naught and x naught plus h, something like this. So except that here we are not dividing through by h because technically it looks like normally, right? If you want to even think about it, you can say f prime of x is equal to, say, what can you say? You can say f of x plus h, right? Minus f of x all over h. Okay, that h is a small thing. So it's now like you have h of f prime of x equals f of x plus h minus f of x. Okay, so this expression now looks like what you call the delta f of x, and that is equal to f of x plus h minus f of x. So that's how we can say we arrive at that expression we have up there. So you can think about it in this way. So that is for the forward difference operator is defined as what we have up there and proven here which I mean I didn't mean to do, but it's fine that I did it. So for higher order, so we can do it for higher order. For higher order forward differences, or higher order forward differences. So we may be required to do higher order forward differences. So in that case, all we just need to do is we already know the delta f of x, right? So we have delta squared now. I don't know if this is delta or nabla. So let me just call it delta for the sake of it. So delta squared f of x is now delta into delta f of x that we had initially. So that means we are going to then have f of x plus 2h minus 2f of x plus h plus f of x. So that is what that is what delta squared f of x would be like. So that's the second derivative. So you may want to cage this. It's really important. Okay. Now, if you take it to the nth place, like if it keeps going, then you now have it in the nth place that the nth derivative of the forward difference is the same thing as the forward difference of nth derivative minus 1 of f of x. So like I said in the next, or is this something I can apply right here? Let me see if I can just apply it here so I don't have to do another video. I think that would be really cool. Let me see. Let me see if I can take an example. It will be lengthy. It will be too lengthy, so I think I would rather do it in another video. So here, let me just establish all these things. Yeah, so if I take examples, it will be pretty long. So that is for forward difference. And then we are good to leave that, move on to another type of difference. So the examples will make it unnecessarily long. So let me leave it until when we come later. Okay, so that's forward difference with that triangle facing up. Then we have number 2, we have the backward difference operator with the triangle facing down. Backward difference operator with the triangle facing down, which I think is nabla, not this, nabla. So forward difference triangle faces up, backward difference it faces down. So I think this is nabla. Let me call it nabla. So the backward difference operator nabla, backward difference operator nabla is given by nabla f of x equals f of x minus f of x minus h. So the same argument can go. You already know that f prime of x for backward difference is f of x minus f of x minus h all over h, right? So if you multiply f prime of x by h, then you get nabla f of x. So this is basically what the backward difference is about. So, I mean, you could use the same arguments to derive it. So, with that said, we can talk about higher order, right? So higher order backward differences are defined. They are defined as, so if you need second derivative, for instance, that's nabla squared f of x. That would be nabla into nabla, careful with this triangle, into nabla f of x. And in that case, that is f of x minus 2 into f of x minus h plus f of x minus 2h. So it's more like reverse of what we had before. Nabla squared f of x is now this second derivative thing. So if you want second order, this is how this goes. Yeah, so f of x minus 2f of x minus h plus f of x minus 2h. So if you go to the nth level, so it means that at the nth level, right, the nabla, so you have nabla, the nth derivative of n, nabla n f of x is simply nabla into n minus 1 f of x. So that is the nth derivative for the backward difference operator. So that takes us to the third type of operator, which is the central difference operator. Central difference operator. Central difference operator, which is like this small delta. Okay. So which is like small delta. So the central difference operator, the central difference operator delta is defined as delta f of x equals f of x plus h minus f of x minus h. So if you follow the argument I made the other time, so that will be like you have f prime of x equals f of x plus h minus f of x minus h all over 2h. So delta f of x now looks like that at 2h times f prime of x. That's what delta 2h looks like here. So that goes. So we say so now for, as usual, for higher order central differences, for higher order central differences, okay, we have delta squared f of x equals f of x plus h minus 2f of x plus f of x minus h, right? So delta squared f of x is f of x plus h minus 2 f of x plus f of x minus h. So the same thing can just go on for everything we've been doing so far. If you want the nth derivative, so of course I've always caged this. So the nth derivative should be something like delta n f of x is equal to delta into delta n minus 1 f of x. Talking about the nth order, nth derivative of the central difference. Now, when we talk about the operators now, from finite difference, numerical integration by finite, using finite difference, right? We had only three things. But in the case of operators, we now have an additional operator, which is known as the shift operator. So we have a fourth type of difference operator called the shift operator, and it plays a significant role. So the shift operator E, that's the shift operator, it's represented by E. So the shift operator E is defined as E f of x equals f of x plus h. Okay, that's like just the function itself, right? So the shift operator f of x is f of x plus h. So we have that as a standalone, but that's not the only shift operator we have. We also have another one. You can also take the nth derivative of it, right? Which is pretty easy. That's the nth derivative of the shift operator of the function of f of x is f of x plus nh now. Okay, that's the shift operator as it is defined. Now, so what does this operator do? This operator helps express other difference operators, other difference operators in a compact form, other difference operators in a compact form. So that's what shift operator helps you to do. So shift operator comes into the play to make you actually see, so it shows the kind of connection between all the operators. So since now we have considered types of difference operators, let's move ahead and look at relationships between the operators. Okay, they can be related. Relationship between difference operators. So what are the kind of relationship that exists between them? So like we said, using the shift operator E, using the shift operator E, the difference operators, the difference operators can be related, as follows. Okay, so the first one, you have that again, let's itemize. We have the forward difference operator. What's the relationship between the forward difference operator and the shift operator? Forward difference operator, forward difference operator. So which is the triangle facing up. So basically, it is delta equals shift operator minus one. Okay, delta equals shift operator minus one. That's the relationship between them fundamentally. And you can take it to the nth level. So this implies that if you expand for higher orders, so it simply implies that delta n is the same thing as e minus 1 raised to power n. So that also subsists. Then that's for the forward difference operator. Then if you take it down to the backward difference operator, backward difference operator, I mean, all of this can actually be proven, all this can be proven, can actually be proven. Yep. Okay. So because if you use their definition, you can prove it. But I don't think I'll just establish the relationships here. So you may want to take time to prove it by just using their definitions. Maybe that'll be the practice question for this session, for this particular video. Backward difference operator. So the backward difference operator is the triangle facing down like this. So its relationship with the shift operator is like this. Backward difference is 1 minus e raised power minus 1. So it's 1 minus the inverse of the shift operator. And that also implies that the nth order of the backward difference is the same thing as 1 minus the inverse of the shift operator all raised to power n. Okay, so that also goes. So that said, we move on to the third one, which is the central difference operator. The central difference operator, that's delta now. So for this, we just have delta. The central difference is equal to shift operator raised by half minus shift operator raised by minus half. Okay, that holds. And then that leads us to the fact that if you take the square of this, if you take the square of the shift operator, I think it makes sense that delta squared will be e raised power minus half minus e raised power minus half raised to power 2. And if you use binomial expansion or whatever you want to use, or I mean, it's straightforward, so we can just expand. We have e raised power half all squared minus 2 e raised power half e raised power minus half, all right, plus e raised power minus half raised power 2. So that makes sense that delta squared is e raised power 1, all right, minus, of course, this cancels this, minus 2 plus e raised power minus 1, basically, and that is the relationship in that situation. Okay, so basically, all we are saying is that this actually has connections with the fact that delta n is equal to e raised power half minus e raised power minus half, e raised power half minus e raised power minus half, all raised power n. Basically, that's what we are saying there. Okay, so that's another connection right there. Okay, so another thing we want to talk about, we are trying to establish relationship between all the methods as much as possible. We have a fourth kind of relationship, which you have everything coming into the mix this time around. having talked about three things, let's talk about the fourth one where we talk about um relationship. Okay, I mean, before we've been talking about them individually as it represent connects to the shift operator. So this time around, let's just talk about forward, forward, or let's say uh so we have a relationship that connects all three. Now shift operator, then forward and backward differences. So there's a connection that also lies there. Forward and backward difference. Okay, I think it's better to even say central difference, right? So let's say shift, okay, shift forward and backward, forward and backward difference operators. Okay, so there's a connection for them too, and that connection is this, that forward difference of f of x is the same thing as the shift operator multiplied by the backward difference of f of x. So that's one nice relationship. And the forward difference of f of x is equal to the shift operator multiplied by the backward difference of f of x. So that also leads us to another so I mean the other aspect of this is that the backward difference, we need to get the triangles right to avoid confusion. So okay, how did I write that? Okay, the backward difference of f of x is the same thing as the inverse of the shift operator multiplied by the forward difference of f of x. Okay, so we have all of that. So that brings us to a conclusion. So we can conclude now that difference operators, difference operators provide, they provide a discrete alternative, a discrete alternative to derivatives, to derivatives and are interconnected. They are interconnected through the shift operator. So the shift operator brings them together. They're interconnected through the shift operator. Okay. So understanding understanding these relationships, these relationships helps in numerical differentiation, in numerical differentiation and finite difference approximations and finite difference approximations. Okay, so that's how that's going to be. We have just established the difference operators and their connections via the shift operator. So the practice question here would be something like this. So I like you to prove the relationships, practice questions. So how many relationships did we establish? We have, this is 1, 2. This is, the basic one is fine. 1, 2, 3. Okay, maybe I should even mark the things I like you to prove. So, so you're going to prove 1, 2, the basic one, that is 3, 4, and 5. Okay. So in that case, I can just say prove, okay, maybe I should say following following the definitions. I mean, what I mean by definition is something like, for instance, uh, if you have the shift operator, the forward difference operator is something like f of x plus h minus f of x. You know, that's the forward difference. So using those kind of definitions, following the definition of each difference operator, of each difference operator, prove prove the fundamental prove the fundamental relationships, prove the fundamental relationships established above. Let me put it that like that. Those five things I marked. So following the definition of each difference operator. So you know the definition already. So I defined the operator initially before I came to their connections. So by following those, I mean, what I mean is by following these initial definitions up here. So these are the definitions when I started out. So this is the definition for forward difference. This is the definition for backward. I mean, not this. This is not basic. This is the definition for backward difference. That's the basic definition. Don't even worry about the square or the nth one. So this is the basic definition for the central difference operator. And this is the basic definition for shift operator. Okay. I mean, this can also come in handy. So following these basic definitions, then prove the ones I marked. Okay. Prove the ones I marked. So, I mean, it will be, you really enjoy it. I remember doing it back in the days and it was really interesting. So you want to try that out and indicate it in the comment section. So just try it out. You will really like it. Okay. Say it in the comment section. Let me also know how helpful these videos are for you. And let me know if you want is a topic you like me to teach or a problem you like me to solve. Okay. Then also indicate I mean, if you have not subscribed to the channel, please go ahead and do that. If you have done that already, thank you so much. Hit the notification bell also so you can always get alerted each time a new video is released. Then like and share so that more people can have access to this great content. In the next video, I'm going to use these difference operators to do some calculations, and you'll see how useful they are because they are really like straight to the point. Till I come your way again, keep doing maths right. Bye.